October 7, 2025, the European Space Agency publishes the first official images of Comet 301 Atlas passing by Mars. The world awaited thrilling details, but instead, a scandal erupted. The photos revealed a blurred point, while NASA, China, and the UAE remained silent. Where are the clear data everyone expected? Why has the most discussed incident in recent years only raised questions and assumptions about what agencies are hiding behind technical excuses? When astronomy enthusiasts with simple telescopes obtain clearer images than billion-dollar missions, and rumors of impossible chemistry start, one thing becomes clear. The real story is just beginning. What are they not telling us? At 9:22 p.m. UTC on October 7th, the first official images from ESA were released through the agency's channels. For several minutes, the most popular science accounts, space enthusiasts, and even meme pages erupted with the same uninspiring shot. Faint blurred dot barely discernible against a backdrop of digital noise. By noon, the hashtag #IsaCasis became a trend in 4 languages, while hashtags like blurred dot and where are the photos flooded platforms X and Reddit, where amateur analysts began dissecting every pixel. Dissatisfaction extended beyond mere disappointment, with comparisons showing that captures from home telescopes had more clear details than a billion-euro Martian orbiter. Comments accused ESA of concealing information, noting the silence of NASA, China, and the UAE. With each unanswered question, the pressure on the agencies only grew. The KSSIS camera, mounted on the ExoMars Trace Gas Orbiter, was not originally intended for observing interstellar objects. Her task was to create clear color maps of Mars's surface, identifying landslides and studying minor changes in dust and frost. When the camera was aimed at the 3I/Atlas, located 30 million kilometers away, its design became a limitation. Each pixel of KSS covers about 340 kilometers, enough to hide entire Martian volcanoes, not to mention a comet's core that may be only a few dozen kilometers wide. The camera resolution, 11.36 microradians per pixel, imposes strict limitations. No matter how perfectly the focus is adjusted or how long the exposure lasts, anything smaller than 1 pixel becomes blurred, and its light smears across the sensor. Nick Thomas, the lead researcher, called it a true challenge, even to simply capture the object. The comet was at least 10,000 times dimmer than the surface features for which KSSIS was designed. The team was assembling exhibits, adjusting tracking, and extracting every piece of signal from the noise. The result, a blurred point, was not an attempt to hide the truth, but reflected technical limitations. A coma of gas and dust thousands of kilometers wide merged with the background, while the core was completely lost. Physics is relentless. At such distances, even the best equipment on Mars can only confirm the presence of a comet, but cannot reveal its secrets. The public wanted a portrait, but the camera could only provide a print. The next hope for details had to come from another tool or completely different orbit. The high-resolution camera HiRISE aboard NASA's Martian orbital spacecraft was supposed to be the ace up Mars's sleeve. Her optics could capture traces of rovers from orbit, and at a distance of 30 million kilometers, it promised at least a hint, perhaps a few pixels, of the core of Comet 3I Atlas. But during the flyby, HiRISE went dark. The government shutdown in the United States, which began on October 1st, halted the entire chain. No communication commands, no status reports, no public data. Official channels fell silent. For several days, both amateur and professional astronomers updated the HiRISE archive, waiting for any signs of activity. Nothing appeared. Even the files with plans that are usually published in advance were absent. With NASA's frozen data streams, attention shifted to other eyes of Mars. China's Tianwen-1 orbiter and the UAE's HOPE mission tracked the comet's approach, but neither published images, statements, or even denials. Silence deepened. Some pointed to the closure as the obvious culprit, but others wondered why 3 space agencies on 2 continents were silent at the same time. In the absence of data, rumors filled the void. Every hour without a response drew more attention to what was missing. It was not just about a clearer image, but also the feeling that the best cameras in the world were being censored. The absence of HiRISE became the main topic of discussion. The missing gem left the internet awaiting external evidence, and every unanswered question fueled suspicions that something was being hidden. In the hours after a blurred image from the European Space Agency went viral, a war of images began. Astronomy enthusiasts from Italy to Japan published their versions, some using deep stacks of dozens of frames, others with AI filters promising to reveal hidden structures. By October 9th, the internet had split into 2 camps. One group claimed to see a clear core, possibly even a hint of a tail or jet, asserting that home telescopes surpassed €1 billion orbital device. Another group warned that each new detail was an illusion, a ghost born from excessive processing and dreams. Maya Treen, a renowned comet hunter from Melbourne, became the unofficial voice of the first camp. She published a sequence of images, each increasingly processed, with annotations indicating what she called irregular trails around the nucleus. Her posts garnered tens of thousands of reposts, fueling speculation about what might have been missed or hidden by professionals. However, professional astronomers countered with comparative images and simulations. They demonstrated how the overlay of weak frames can amplify background noise, turning cosmic rays and hot pixels into false structures. They argued that using artificial intelligence only makes the artifacts clearer, but does not improve scientific results. The debate quickly became technical. Terms like sigma clip-in, deconvolution, and pareidolia became popular on forums as users tried to uncover the truth from raw data. Some noted that even a perfect stack of images at a scale of 340 kilometers per pixel could not resolve a comet's core of such size. The clearest images obtained by amateurs often relied on aggressive processing, raising more questions than answers. With each new processed frame, the line between discovery and illusion became increasingly blurred. The thirst of the internet for details exceeded what the data could honestly provide, and the demands for strict, transparent analysis grew louder. If there was anything, it would require more than just software tricks to prove it. Anonymous messages began circulating even before the first footage from the European Space Agency concluded its discussion. As rumors spread, demands for real data grew. The thirst for answers on the internet now depended on the next round of measurable facts, trajectory calculations, radio signals, everything that could be tested. Until then, the burden of proof remained on the claimants, not the skeptics. Mallory Lefland, the mission shift leader of Perseverance, faced a problem that was not on the standard mission checklist. The rover's navigation camera was not designed to track comets, especially one speeding past Mars at nearly 90 kilometers per second. But on October 7th, she authorized a special sequence, 10 minutes of continuous exposure of the sky in hopes of catching the trail of Comet 3 Atlas as it streaked across the rover's field of view. The initial frames showed only a barely noticeable dot. It was slightly wider than a pixel and stretched diagonally across the image. At first glance, it looked like a digital glitch or a cosmic ray, but the timing coincided with the predicted passage of a comet with a few seconds margin of error. The mathematics behind the blurring was simple, but its consequences were not. At a speed of 90 kilometers per second, Comet 3 Atlas will cover about 54,000 kilometers in 10 minutes, the same length as the trail from the navigation camera. If the exposure lasted the entire sequence, the trace matched the motion blur model, a distant object moving quickly, too faint for a single frame, but visible as a blur when integrated over time. But there was one nuance. If the camera made a short exposure, the source must have been much closer, possibly even in orbit around Mars, to create such a long trail. Without access to the original FITS headers, the exposure time and its frequency remained locked in the rover's vaults. Every calculation depended on this missing detail. Was it a comet, or a nearby object flashing in the sky? Lefland's decision turned an uncertain rumor into a verifiable statement. The trace of the navigation camera became the first solid number in a sea of speculation, a question at the level of 54,000 kilometers. For the next round of listening to radio signals and checking trajectories, the mathematics would set the bar for what would be considered proof, and what was merely noise. The line drawn from the crater lake on October 7th pointed almost directly to a spot in the sky known for only one thing: the WOW signal. In 1977, a radio telescope in Ohio detected a 72-second signal at a frequency of 1420 megahertz, known as the hydrogen line. Its source was never found, but the coordinates remained in the memory of researchers searching for extraterrestrial life. Now, as the comet 3I/Atlas passed just a few degrees from this area, the coincidence became too noticeable. Forums filled with unofficial calculations. To match the power of the WOW signal from a transmitter located 600 astronomical units away, at least half a gigawatt would be needed, or maybe 2, if the antenna were directed straight at Earth. This is equivalent to the power of a large power plant directed through the abyss of space. However, despite all the discussions, no public observatory has published data on the hydrogen line from the comet's passage. There was neither a coordinated listening campaign nor raw spectra, not even 0 results. Silence became not only visual, but also radio signal. The air was filled with the question: given the geometry and calculations, why had no one conducted the simplest test? On October 29th, the comet 3I/Atlas vanished behind the sun from Earth's perspective, lost in such bright light that even the best telescopes could not detect it. For nearly 40 hours, no ground observatory could track it. The angle of solar deviation of the comet decreased to critically safe levels only for the most protected instruments. During this dark period, every theory found an opportunity for development. Some astronomers warned of natural emissions or possible destruction, which usually happens to comets under solar pressure. Others, studying orbital models, wondered aloud if some maneuvering, something artificially created, was happening away from the eyes of observers. The Galileo Project, a team searching for signs of unnatural technology, announced round-the-clock monitoring of all available radio and optical channels, hoping to detect any anomalies as the object approaches perihelion. The main event remained hidden, leaving the world only with models and speculations. When the 3I/Atlas reappeared, its brightness, trajectory, and any new fragments became the next test for both the unpredictability of nature and the limits of human observation. The beginning of November brought a list of tests for Tri-I/Atlas. Astronomers turned to brightness curves in search of sharp drops or spikes that could signal fragmentation. Orbital models based on new data were tested for small deviations, evidence of jets, gas emissions, or something stranger. Each measurement was either successful or failed. Did the comet's glow dim as expected, or was it breaking into fragments? Trajectory forecasts were compared with reality in search of unexpected changes. Meanwhile, the JUICE spacecraft awaited its observation window later this month. Its instruments promised a new perspective on the situation, but raw data wouldn't reach Earth until deep into the year 2026. Until then, every change in the comet's path or brightness becomes a clue, and every delay in data release keeps the world in ignorance of what has endured solar exposure. The October sky did not belong solely to Tri-I/Atlas. Just a few days before the comet's flyby past Mars, the celestial body registered as number 2025, TF, slipped past Earth, entering the orbits of Global Navigation System satellites without any warning. This asteroid, just a few meters wide, managed to evade detection by all major observatories until it was almost directly above us. It reminds us that even in the era of comprehensive monitoring, small and fast objects can remain invisible. Meanwhile, two comets began to follow their unpredictable paths. Comet C025A6 Lemon started to glow brightly. A few weeks before the expected time, this hinted at a possible eruption. Comet C0025 R2 soon attracted attention with its close approach, just 0.26 astronomical units from Earth, raising hopes for a visible tail and concerns about sudden fragmentation. Each of these events highlighted the limits of modern observation, where the next surprise can come from any direction and in any scale. The lesson is that the cosmos is full of dangerous approaches, and our observation is never complete. On October 7th and 8th, 2025, the European Space Agency released the first official images of three comets known as I/Atlas, represented by just a single blurry pixel, sparking global debates and calls for transparency. The low image quality was explained by the technical limitations of the Cassini device, not by intentional concealment of information. However, the simultaneous silence from high orbital devices like Tianwen-1 and HOPE left some key data unexplained. Despite viral images from astronomy enthusiasts and persistent rumors of unusual emissions or precise maneuvers, no official evidence has confirmed these claims. The navigation camera, Perseverance, captured a blur corresponding to the expected movement of an object traveling at 90 kilometers per second, but alternative explanations could not be completely ruled out. When I/Atlas disappeared behind the sun at perihelion, observers noted the beginning of November in anticipation of signs of fragmentation or changes in trajectory. The delayed observations of the JUICE spacecraft and the recent close approach of Celestial Body 2025 TF highlight ongoing issues in monitoring fast and unpredictable objects. To this day, the true nature of I/Atlas remains unsolved, highlighting both the limitations and urgency of open data in planetary science.